This is a general disclaimer. Redlands Community College attempts to have the most accurate and up-to-date information listed in its content and delivery. However, your education is your responsibility. Redlands Community College or Roy Smith makes no guarantee in the accuracy of this information in this video and accepts no liability for the informational video. The information expressed is strictly the opinion of the author and the presenter, which is listed in the reference near the end of the video. This information is designed to supplement your own education or initial education and should not be used to replace any current academic program you're enrolled in. View the information and content at your own risk. Thank you.
This is going to be lab interpretation part 3, and we're going to start this part off by talking about glucose metabolism tests. So blood glucose, or whole blood versus serum. Whole blood on males and females, average before meals would be 80 to 120 milligrams per deciliter, and the average at bedtime should be about 100 to 140. And the plasma, male and female, average before meals 90 to 130, and the average at bedtime about 110 to 150. This helps us determine whether or not someone might be diabetic. Two types of diabetics, type 1 and type 2. Type 1 would be insulin dependent, so your body does not make enough insulin to make things happen. A type 2 diabetic is increased cellular demand and an insulin resistance from the cells. So your body still makes insulin, it just doesn't make enough of it, and it doesn't make an efficient version of it to your cellular environment. A glycohemoglobin, or hemoglobin A1C. Glycohemoglobin forms in periods of prolonged hyperglycemia. So if you have high blood sugars for a very long time, you're going to form glycohemoglobin. Measures the percent of saturation, indicates a trend over the last 3 to 4 months. So it kind of looks in the past and it tells you whether or not your sugars have been good during that time frame. Normal values for male and female. In the non-diabetic, about 4 to 6%. In diabetics, we look to target them less than 7%. Good control, less than 7.5%. Fair control, 7.6 to 8.9%. Poor control would be greater than 9%. Lipid metabolism test. This is going to talk about cholesterol. It's related to how much fat you eat in your diet. So the normal for male and female, desirable would be less than 200 total cholesterol. Borderline high, 200 to 239, and high would be over 240. High levels, cause is often unknown, could be dietary, hereditary, pregnancy, pancreatic problems, low levels, hyperthyroidism, severe liver damage, and malnutrition. This test also gives us a glimpse at how much cholesterol is hanging around. The greater content of cholesterol that hangs around, the greater chance that you have of making atherosclerotic plaques. Triglycerides. Normal male and female, desirable would be less than 150. Borderline high, 150 to 190. High, 200 to 499. Very high, greater than 500. Again, high levels, probably dietary, hereditary concerns, pregnancy, pancreatitis, alcohol abuse. Low levels would suggest malnutrition or medications. They have you on too many anti-cholesterol meds, if you will. Lipid metabolism continued. This is HDL, or high-density lipoproteins. Normal, positive cardiac risk factor, and HDL less than 35 milligrams per deciliter. I'm going to pull this out here. Total cholesterol to HDL ratio in men, 5, and in women, 4.5. Negative cardiac risk factor would be an HDL greater than 60 milligrams per deciliter. This is the good cholesterol, by the way. High levels, moderate alcohol intake, exercise, or weight loss. So if you have high levels, that's what will probably be the cause of it. Low levels, diabetes mellitus, menopause, or obesity. LDL, normal, 160. This is what's considered, even though it's not bad cholesterol, it's considered the bad cholesterol. Low density lipids, normal 160 milligrams per deciliter in male and female. High levels would be a high fat diet, hyperthyroidism, nephrotic syndrome, diabetes mellitus, familial lipid disease, low levels, advanced liver disease, or malnutrition. It's going to talk about cardiac enzymes. CK measures creatinine kinase. Now, what creatinine is high levels of this would indicate muscle damage. Now, this is a non-specific test. This just says if your CK is high that you've had muscle damage. Whenever we get to the isoenzymes here in a second and start talking about them more, those are going to be more cardiac specific. So normal men 60 to 100 units per liter, and women 40 to 150 units per liter. Isoenzymes, CK1, CK2, CK3. It's the MB fraction that we look at for cardiac specific. So we should see an isoenzyme, and that's what they're called, of CKMB less than 3%. High levels mean muscle disease. Rhabdo is a possibility with high levels of CK. You've done a lot of exercise. You've had an IM injection. You're in shock. You have tumors. Low levels have no clinical significance. CKMB measures creatinine kinase myocardial band. Normal in male and female, less than 10 units per liter. MI is improbable. You probably are not having an MI. 10 to 12 units per liter is inconclusive, and greater than 12, an MI is probable. High levels of this greater than 12 would suggest that you have myocardial damage. Low levels have no clinical significance. CKMB. LDH measures lactase dehydrogenase. Again, this is an isoenzyme, and these two right here are the ones that we're going to look at for this isoenzyme and this cardiac marker. Normal on an adult is 40 to 90 units per liter. The isoenzyme, if everyone will notice that LDH1 is less than LDH2. Well, if you have an MI, that flips that ratio to where LDH1 is more than LDH2. So, very simply, one more time, LDH1 and 2 are looked at for the isoenzymes. LDH1 is generally less than LDH2. If that is flipped and LDH1 is more than LDH2, it is suggestive that you might have an MI. High levels, anemias, elevated LDH1 and 2, pulmonary embolism, elevated LDH3, liver damage, elevates LDH4 and LDH5. An MI causes a reversal of LDH1 and LDH2 ratio. Low levels have no clinical significance. Myoglobin measures myoglobin. Normal in male and female is 50 to 120. Myoglobin is inside of the actual muscle cells. It's what gives the muscles themselves their reddish tint. Normal is 50 to 120, and the EG is an ELISA grams per deciliter. High levels would say myocardial necrosis, or rhabdo is another possibility, and low levels have no clinical significance. Troponin measures troponin. Troponin is right pretty close to the myosin head of the thin and thick filaments in the muscle cell. So it's an intracellular component of muscles. Now, cardiac enzymes specifically have this. So this is cardiac specific. In the normal in male and female, a troponin 1 less than 0.6 nanograms per milliliter is normal. A troponin of 1.5 nanograms per milliliter is suggestive of an MI. It would come from the intracellular compartment. So at the point that we have an infarct and are spreading that cellular material, we should be able to see that in the blood sampling. Troponin T greater than 0.1 to 0.2 would be suggestive of an MI. High levels say that you have myocardial necrosis. Low levels have no clinical significance. BNP, or brain natriuretic peptide. Normal values in the male and female are 50 to 100. However, these are stretch peptides that are in the ventricular muscle. So as the ventricular muscle gets stretched, we may have higher levels. So abnormal ventricular function, and this would be from a very large heart, or congestive heart failure, we would see high BNP results. So greater than 300 to 500, and it would depend on the reference lab. It might be suggestive that someone is in congestive heart failure. Low levels have no clinical significance. Liver function tests, amylase. Measures amylase. Normal value in male and females is 53 to 123 units per liter. High value would suggest pancreatitis or pancreatic trauma. Amylase itself degrades carbohydrates, and it gives us a good look at pancreatic function. Low values would suggest that we have pancreatic destruction. Lipase. Measures lipase. This will assist in breaking down fats or emulsify fats. Normal value, male and female, 3 to 19 units per liter. High value would suggest pancreatitis again, or pancreatic trauma. A low value on the lipase has no clinical significance. Serological testing, broad area of laboratory analysis, and it doesn't only include just these areas, but these are the areas we're going to talk about, which are included are called blood banking, endocrine tests, and then microbiology. In blood banking, several common tests for matching blood before it's administered. One of those is the ABO blood typing, an RH factor, and this would be positive or negative. Most of us know our blood types by A positive, O positive. Well, the positive or negative is actually the RH factor. A direct Coombs test, which measures the antibodies on the red blood cell's surface. So we do not want to have an antigen-antibody reaction. And an indirect Coombs test, which measures the antibodies to the red blood cell in the blood serum. So in the serum itself, not the formed elements, does this person already have antibodies present that will attack the other person? So good things to know before giving someone a blood sample that's not theirs. This is the blood typing, and a quick overview of this, that we worry about the surface antigens that are present, and we also worry about the antibodies that are present. So an example of this, type A blood, on the surface of it is saying I am A, and that's what the antigens state. It also has antibodies already prepared to fight against B blood. So if you introduce B blood to someone that has A blood, very simply these antibodies are going to have an antigen-antibody reaction on the surface of the red blood cells. And type B surface antigen is B, I am B, and anti-A antibodies. So it will cause a fight very quickly with type A blood. Type AB has the surface antigens for both A and B on it. This would be A and this would be B. But it has antibodies for neither. So it will not pick a fight. Universal recipient is going to be AB negative. And the reason I say negative is because then it wouldn't even bring in an RH factor. There is no RH problems there. RH is a specific different type of blood test that we do on them that identifies if they are RH positive or RH negative. If they're positive, then they have the antigen. If they're negative, then they do not. Type O, last but not least, it doesn't know what it wants to do with its life. On type O blood, there are no surface antigens, but it has antibodies for both. So the universal donor is going to be type O, and the universal recipient is going to be AB. AB can take anybody's blood. I said that opposite just there for a second. AB positive would already be exposed to the RH factor. So they could take both AB negative and AB positive. This is what happens in the cellular compartment if we get the wrong blood typing. We have an antigen-antibody reaction, and it could lead to hemolysis, which is breaking down of the red blood cells. Endocrine test. We're going to talk about cortisol, TSH, T3, T4. Cortisol measures the adrenal cortical function of the person. So if they were having hyperadrenalism or hypoadrenalism, the values would be messed up on this. Normal values for cortisol are 5 to 25, and these are lysograms per deciliter. High values would say Cushing syndrome or hyperadrenalism, or maybe a pituitary tumor. Low value would say Addison's disease or hypoadrenalism. TSH, thyroid stimulating hormone, and that's what this test does, is it measures the amount of thyroid stimulating hormone that we have available in the body. Normal values for both male and female should be 0.5 to 5 ELISA units per milliliter. A high value would say that they were in thyroid failure because the TSH didn't get used up and the thyroid didn't respond to it. Or you could have a pituitary tumor that just kept secreting TSH again and again. Low value, hyperthyroidism, or pituitary failure. T3 measures triiodothyronine. It's a lot easier to say T3 on that. Normal values for male and female are 60 to 180 nanograms per deciliter. High values of this thyroid hormone would suggest hyperthyroidism. Low values would suggest hypothyroidism. Now, since the thyroid hormones increase metabolism systemically, we might get somebody that looks like they're about ready to come out of their skin, or thyroid storm, presents with hypertension, tachycardia. So just be aware of that. It could be nothing more than a high amount of thyroid hormones running around in their body. Assessment. Total T4 measures L-thyroxine, normal values for male and female, 4.5 to 10.9 ELISA grams per deciliter. High value, hyperthyroidism. A low value is hypothyroidism. Again, on all of these numbers, please pay attention to the reference laboratory's values. Free T4 measures free thyroxine. Normal values for the male and female, 0.8 to 2.7 pg per deciliter. High value, hyperthyroidism. Low value, hypothyroidism. Thyroxine would be in the stimulating factors of the thyroid gland, so if we have a bunch of it there, the thyroid gland isn't functioning appropriately, or if we have not enough, there's not enough thyroxine running around. Microbiology. We're going to talk about gram stain and a Kirby Bauer. So what a gram stain allows us to do is it allows us to identify the bacteria. Culture placed on a microscopic slide. Reagents are introduced to the culture, crystal violet and Graham's iodine solution. The microorganisms take up the stain based on the nature of their cell wall. And the slide is then examined under a microscope. So we come up with characteristics of that cellular environment. After applying all of these materials to the slide where the bacteria is located at, we know if they are gram positive or gram negative, and it helps us identify what type of bacteria it is. A gram positive will stain purple, and a gram negative will stain red. Kirby Bauer is an antibiotic susceptibility test. Now, what this shows us is if each one of these represented an antibiotic, we essentially put the bacteria onto this media and grew some of it, and then put these discs on there. And that's what each one of these discs do, is they represent a certain specific type of antibiotic. So by looking at this, we can see growth or non-growth. And what an antibiotic does, very simply, is it sets up an environment in the body to where it will not allow the bacteria to proliferate. So with that said, this bacteria is not susceptible to C. It is not susceptible to A. However, if I wanted to get rid of the bacteria that's running around the system, this is the one that I would choose, because none of the bacteria grew into the area where E had set up shop. Physiological testing, and we're going to talk about arterial blood gases. So we're going to start off with pH. pH measures the blood acidity, and the body only lives at a certain specific pH, which is 7.35 to 7.45. If we're out by 1 point in either direction, it is life-threatening. High values on this, so if they were 7.5, they would be alkalotic. Low values, like a 2.0 or a 6.0, below this range, would make your patient acidic. PaCO2, it measures the partial pressure of carbon dioxide in the blood. Now, this is just like anything. If you're building a blue tower out of Legos and you have 500 blue Legos, very simply, you have quite a few Legos to build the blue tower with. Same one with CO2. CO2, the more building blocks that are retained within the body, the greater chance of your body creating an acid out of this. And the acid's called carbonic acid. The normal levels in the blood system are 35 to 45. High values would suggest respiratory acidosis and low amounts of ventilation. If you can't blow off the CO2, it will retain itself. Low values would suggest respiratory alkalosis and hyperventilation. We've blown off too much CO2. PaO2 measures partial arterial pressure of oxygen in the blood. Normal values for this are about 80 to 100. This should correlate as well with our pulse oximetry readings that we're getting. High values would mean over-oxygenation or hyperventilation. Low values would mean hypoxia and hypoventilation. And this is oxygen, the amount of oxygen that's in the arterial sample. HCO3, and I'm going to go over this once and we're going to talk about it again before we get out of the slide set. Measures the bicarbonate ion concentrations in the blood. Now, bicarbonate is awesome. That it will pick up an extra hydrogen molecule. Now, this is no longer bicarbonate, it's carbonic acid. The red blood cell houses an enzyme on it called carbonic anhydrase. It will break this down very rapidly if necessary. To water and CO2. The CO2 is expelled from respirations. The water goes to the kidneys to be eliminated. So our body very easily can eliminate the acid. High values of bicarbonate means that we are too basy or too alkalotic. Metabolic alkalosis could be happening, or bicarbonate ingestion could have occurred. Low values says that we have a base deficit. We do not have enough bicarbonate to handle things. It may be suggestive of metabolic acidosis or an increased serum chloride. Chloride shifts occur at the red blood cell and can adjust this. SaO2, or pulse oximetry readings, measures the hemoglobin oxygen saturation. Now what this does is this is a light that takes a look at the hemoglobin molecule and it says, are you saturated or not? 95 to 100% on pulse oximetry readings is what we should get. High value has no clinical significance. A low value suggests that we are hypoxic or have had a hypoventilation. One other thing I want to add on this. The machines cannot tell the difference unless you have a special machine that looks for carboxyhemoglobin. If the hemoglobin molecule is loaded with oxygen or CO. If it's loaded with CO, your pulse oximetry readings could be 100%, but that is not what you're delivering to the cellular environment. Arterial blood gas is continued. Hemoglobin measures blood hemoglobin concentrations. Normal value for male and female are 12 to 18 grams per deciliter. A high value on this would suggest dehydration. We've concentrated the sample. Or they could be polycythemic from continuous hypoxia in the long term or chronic hypoxia. Low values could be overhydration. We've diluted the sample too much. Anemia, they don't have enough formed elements in their blood. Or hemorrhage, we bled out somewhere. So let's talk about all this together here really quick. We live with a pH of 7.35 to 7.45. If we're out by one whole point, like 6.35, or 8.35, 8.45, my apologies, it is not survivable in any form or fashion. If we have extra components or parts, the extra components and parts will make up building blocks. Now, an example of this, if there's an excessive amount of CO, then, or CO2, then very simply your body will not store all of the CO2 at the cellular level. The easiest thing for it to do is to find a water molecule and turn it into carbonic acid. So let's talk about our first acid-base derangement. A pH of 7.35. So anything less than 7.35, they are going to be acidic. So I already know it's acidosis, I just don't know what kind yet. This one has an increased PaCO2, which would mean that it was greater than 45. This would be more building blocks. It is suggestive at this point right here that the patient is in respiratory acidosis. However, last clincher on this, an increased HCO3, 24 to 30. So a bicarbonate level greater than 30 is what I should see in this, and this would be suggestive of respiratory acidosis. Quick breakdown. Step 1, are they acidic or alkalotic? In this case, they are acidic. They are less than 7.35. Increased PaCO2. So they have more than enough building blocks to make carbonic acid, and an increased amount of HCO3. So with these two building blocks present, it is respiratory in nature. Respiratory alkalosis. This is alkalotic. This means that their pH is going to be greater than 7.45. So they are alkalotic. And for the respiratory version, they are not going to have enough CO2 in the sample. So they're going to have a decreased PaCO2 or less than 35. And they're going to have a decreased HCO3 or less than 24. By the steps, are they acidic or alkalotic? Well, they're alkalotic. Why are they alkalotic? Well, they don't have enough CO2 to maintain the bicarbonate buffer system, or they don't have enough CO2 to maintain enough carbonic acid to adjust the acid base. So it is respiratory in nature. Very simply, if you're identifying respiratory acidosis or alkalosis, the first question you should ask is, are they acidic or alkalotic? The next question you should ask, does it have anything to do with CO2? Metabolic acidosis. This one here is going to be less than 7.35. So they're going to be acidic. Decreased HCO3 is going to be your telltale sign. The reason being is they don't have enough bicarbonate to pick up the extra hydrogen ion and make H2O and CO2 to eliminate the acids. So at the point that they have a decreased bicarbonate, they don't have enough base to go around. So decreased bicarbonate and a decreased PaCO2. Now normally, if we have a decreased amount of carbon dioxide, it should make us have a respiratory acidosis. So this here, the decreased PaCO2, is giving us the wrong picture. So they are acidic. It has nothing to do with CO2. So it must be metabolic or another third-party acid. Okay, metabolic alkalosis. They have a pH greater than 7.45. Okay, metabolic alkalosis. They have a pH greater than 7.45, so they're alkalotic. They have an increased amount of bicarbonate and an increased amount of PaCO2. Well, this normally would give us an acidotic state. In this case, since we are alkalotic, it has to be from a third-party acid or a metabolic alkalosis. Conclusion. Hematological testing gives the caregiver a viewpoint to the formed elements and the coagulation factors of the blood. Chemistry gives the caregivers an inside look at the chemical processes of the body. Cardiac enzymes give a real-time look and assessment for damage to the myocardium. Serological testing gives the caregiver a good assessment tool to identify antibodies already present from disease as well as blood typing and matching. Microbiological sampling allow the caregiver the ability to see the type and sensitivity of the microorganism present. Physiological testing gives the caregiver an overall look at the acid-base balance of the body as well as gases available to the cellular environment. References for this chapter were taken from the American Academy of Orthopedic Surgeons, AAOS, American College of Emergency Physicians, and this is from the Critical Care Transport Manual. If you have any questions concerning this section, please feel free to give me a call. My name is Roy Smith, smithr@msa.net, or 405-219-7613. Thank you.